All right, and this is going to be our last video here. This deals with geometric series. So just like in the previous video, we were talking about arithmetic sequences. We have a geometric sequence as well. Now, what makes this different is the arithmetic sequence deals with addition or a common difference, and the geometric series deals with a common ratio. So uh, the geometric sequence is a sequence of the form, and this is going to be right here. That's our first term, second term. So a times AR to the first times AR to the second times AR to the third, and so forth, where A is the first term and then R is what we call this common ratio. Now, the nth term, meaning in general, of the geometric sequence is going to be A sub n equals A times R to the n minus 1. So, a really easy example of something like this would be an example where we have, let's say, if A equals 2 and R equals, we'll say 2, then we're going to have the following geometric sequence. 2 times, and I like to do this myself, 2 times 2 to the 0 for the first term, 2 times 2 to the first, 2 times 2 to the second, 2 times 2 to the third, and so forth. So this turns out to be our first term, which is nothing more than just 2. This is going to be 2 to the second power, which is 4. And this is going to be 2 to the third power, which is 8. And then 16, and so forth. So let's look at another example here where we're going to have to actually find what the geometric sequence looks like. So in this example, we're going to determine the common ratio, we're going to determine the fifth term, and we're going to determine the nth term of this geometric sequence below. Now, sometimes geometric sequences are really easy to see, and then other times they're definitely not that easy to see. One of the things that you can try to do is try to look at it and say, okay, is there anything that we have here in common? So the way that I like to look at this is this 2 really doesn't help us that much. It will once you see what I do a little bit later, but right now, the way that this looks, it really doesn't help us. Now, the 6 is really 2 times 3, all right? In other words, I factored a 2. Now, the 18, well, that's really 2 times 9. And then the 54, well, that's really 2 times 27. So if you can look at this and you kind of take a step back, notice that we have a 3, we have a 9, which is really 3 to the second, and then we have a 27, which is really 3 to the third. So now when you look at this, that 2 is really 2 times 3 to the 0. So our geometric sequence here, all right, our geometric sequence, A sub n, oh, I hate that when that happens. So our geometric sequence, A sub n, is going to equal 2 times 3 to the n minus 1, where our common ratio is equal to 3, okay? So we did find the nth term of our geometric sequence, so that's done. The common ratio is done. It's a 3. So now all we have to do is just find our fifth term. So this is going to be A5 equals 2 times 3 to the 5 minus 1, which is going to be A5 equals 2 times 3 to the 4th is 81. So our fifth term in this sequence is going to be 162. So just like in the previous video when we talked about Gauss, there's somebody else here that I think we should really talk about because this person, Einstein actually credited this person with being the most influential and important genius when it comes to mathematics of the 20th century. And that person is Ramanujan. Ramanujan was born in India back in 1887. You can read this. And one of the discoveries that Ramanujan came up with is a way to estimate what pi is using a series. So you could look here, and this is the series that Ramanujan used for estimating pi, or 1 over pi in this situation. All right. But what makes Ramanujan so unbelievably important to the field of mathematics is his idea of being able to prove things and his approach to proving. See, Ramanujan grew up in a very small village, very poor, and his genius was just completely raw. It was amazing what he would come up with, and he had a notebook full of just all these beautiful math proofs. And to this day, there are still some mathematicians who just they look at this and they go, it's unbelievable the way that Ramanujan thought and how he approached problems in terms of in terms of what the course of mathematics is actually doing. Another person like that is called Pierre De Fermat, or Fermat's last theorem. All right. And I would highly suggest that if math interests you a little bit and you're really interested in the people who are responsible for math, I would look up Fermat and I would look up Ramanujan, because their contributions to mathematics is unbelievably interesting. And on top of it, both Pierre De Fermat and Ramanujan were not classically trained mathematicians. They did math on the side for fun. Like, that was one of the things that they did. So I highly recommend looking into these two mathematicians along with other mathematicians as well. So the next thing that we're going to be looking at here, all right, is going to be, let me get out my pen real quick. We're going to be looking at partial sums, just like in the previous video, partial sums, but instead of arithmetic sequences, we're going to look at geometric sequences here. All right. So an easy way to kind of look at this, all right, is let's say we have the following. So we have the partial sum of some series where k equals 1 to n of a times r to the k minus 1. So this is our geometric sequence. And we know that the terms are going to look like a, and then ar, and then ar to the second, ar to the third. And we will keep doing this all the way up until we get to ar to the n minus 1. Okay? Now, if we approach this the same exact way that we did the previous using Gauss's method, then what we're going to have here is the partial sum for just a regular geometric series. So let me write this out real quick. And then if we take another series and we multiply it by if we take our series and then we just rewrite this so it kind of goes backwards a little bit, but we're going to multiply it by r, here's what we get here. And I'm going to kind of stagger this a little bit so you can see how everything works out. And I subtract these two. All right. So what I'm going to get is the sum minus r times the sum equals, you're going to notice that all of these terms all cancel out. And the only ones that are left over are going to be a minus ar to the n. Now, if we take this and we solve it, what we can do is we can say, well, notice here, we have Sn, so we can factor that out to give us our partial sum times 1 minus r is equal to a, and notice here, we can factor out an a. So we're going to get a times the quantity 1 minus r to the n. And then finally, dividing both sides by 1 minus r gives us our partial sum of a geometric series, which is equal to the first term a times 1 minus rn all over 1 minus r. And this will always work as r does not equal 1. Okay? So your book does a pretty good job at just explaining what this is in a little definition box. Let me go ahead and copy and paste that. All right, there we go right here. And it's just basically the same exact thing that we have right here. I just proved it to you. That's all. So we can use this to go ahead and solve partial sums of any geometric series. So let's go ahead and let's look at the first one here. We'll do two little examples. So here's our first example. Let's find the partial sum to 1 plus 4 plus 6. And we're going to go all the way up to 4,096. All right. So initially, what's really easy is we know A equals 1. So we know in our partial sum, let me write out the formula real quick. We know in our partial sum right here, A is going to be equal to the value of 1. Now let's go ahead and let's look at our geometric sequence here. So notice here we have a 1. Here this is like 4 to the first. Oh, hold on. I have a typo here. This is supposed to be 16. I'm sorry. So now this makes so much more sense. This will be 4 to the second. And if you could see here, we definitely have our common ratio, which is equal to 4. All right. So we can easily find the partial sum of the sequence here. So let's see here. How many terms are there in between 1 and 4,096? There are 7 terms. So like 4 to the 0, 4 to the first, 4 to the second, 4 to the third, all the way up to 4 to the 7th. So I'm going to leave that up to you to go ahead and figure that one out. Okay? So we have the partial sum of the 7 terms is going to equal 1 times 1 minus 4 to the 7th all over 1 minus 4, which equals 5,461. So the partial sum is 5,461. So like I said, it's very straightforward. Make sure you understand how I got that value right there. Okay? Actually, this should be 4 to the 6th. Okay. So let's go ahead and let's look at one more problem here. So this is going to be another one. We're going to find the sum to the summation from k equals 1 to 6 of 7 times negative 2 over 3 to the k minus 1. All right, so here, another one, really straightforward. So the given sum of the 6 partial sum is going to have the first term, a equals 7 times negative 2 over 3 to the 1 minus 1, because k is starting off at number 1. So this just turns out to be a equals 7 times negative 2/3 to the 0, which means a equals 7. So here's our first number in our sequence, all right, or in our series, all right? Now, we have all the information we need, because if we look right here, let me go back, let me scroll up right here. If we look right here, this negative 2/3, that is our common ratio that we have. So here's our common ratio. It's already given to us. We just had to read it. So if we add up from 1 to 6, so we're starting at 1, we're ending at 6. So the 6th partial sum is going to be equal to 7 times 1 minus negative 2/3 raised to the 6th power, all divided by 1 minus negative 2/3. And I'm going to go ahead and let you use your calculator for this. But what I came up with when I used, my answer fraction in my TI-84 calculator is 931 over 243, which is approximately 3.83 if I round to 2 decimal places. So that's going to be it for this video. Very straightforward stuff. There's a lot more that goes into series, especially geometric series, such as infinite series, and ways to write decimals. Also geometric series using fractals and everything. I mean, there's so much to just series. You could actually, you're going to. Once you hit Calc 2, you're going to start to see a lot of these series representations within the calculations that you do. And any higher order mathematics always deals with series in some fashion, like the Fourier series, Taylor-Maclaurin series, stuff like that. So good luck, and we got a couple weeks left. So good luck, and if you got any questions, let me know. See ya.